Bismillahirrahmanirrahim. Assalamu alaikum and welcome to the second session on control charts. During this session, we'll be doing all these charts for shift and dispersion. Control charts are best understood with examples, but before I take the first example, two important points. First point is what is meant by making or creating a control chart. It essentially involves 5 steps. The first step is to apply the formula for that chart and find the center line or the mean of the chart, the upper control limit, and the lower control limit. Sorry for the typo over here, it should be lower control limit. Then these limits, center line, upper control limit, and lower control limit are to be plotted on the chart. Then plot the sample data on the chart, join the data with a line, and finally interpret the chart that is indicate if the process is under control or it went out of control at any stage. The other point was on this chart, which you saw earlier also. I had said that control limits are essentially center line plus minus 3 sigma. Insofar as control charts for shift and dispersion are concerned, sigma is predetermined or pre-calculated through a system of coefficients. We'll see that when we actually do these questions. In case of defects and defective charts, of course, the sigma has to be worked out depending upon the formula. Of course, every chart has its own formula for working out sigma or dispersion. With that, we can start our first chart, which is X bar chart, X bar R chart, and the R chart. One thing more to remember is that shift and dispersion are essentially the flipped sides of the same coin. One does not exist without the other, and it is always good to always create both the charts together, put them one above the other so as to correctly interpret the data. It's no use trying to find out shift without considering dispersion, and it's no point trying to find out dispersion without considering shift. So both go hand in hand, and that is what we are going to do in this first example also. The case is that masonry blocks arrive at the project site by truckloads and are placed into a pile. A sample of 5 blocks is taken from the pile and tested for breaking strength in tons. 6 truckloads have so far arrived. Develop shift and dispersion charts for 3 sigma process. And then testing observations are as follows. 2 points. One, it says a sample of 5 blocks. That means the sample size is 5, or small n is equal to 5. Then it says 6 truckloads or 6 piles, which essentially means that there are 6 samples. It says 3 sigma process, but even if it is not mentioned, then it is understood that it is a 3 sigma process, because we know that 99.7% of the results or data lie within 3 standard deviations, therefore 3 sigma. And here is the data. These are the samples. These are the 5 blocks from each sample, and these blocks were taken for a test, breaking strength test, and these are the results. This block collapsed at 0.96 ton, this block collapsed at 0.8 ton, and so on and so forth, and we are required to develop the appropriate control chart. The sample size here is 5. That means it is less than 10. So we will be going for X bar chart with range for shift and range chart for dispersion. This is how we normally do it. This is the same data, and against data, we put another two columns. This column is headed sample mean or X bar, and that's where the name X bar chart comes from. So X bar. This is a simple mean of the sample. So you add all the 5 and divide it by 5. Of course, on a spreadsheet, it is very easy. Manually, it does take some effort. We calculate the sample means of all the 6 samples, and then take their mean again. So this sigma bar, this X bar, because we are taking its mean again, it becomes X double bar, or mean of the mean. So when we take mean of the mean, we get 0.937 tons. The next column is for range. Range is the difference between the maximum value and the minimum value of the sample. So it's another measure for dispersion. In this particular sample, the maximum value is 1 ton, and the minimum value is 0.8 ton. So the range is 1 minus 0.8, so 0.2 ton is the range, and at the end of the column, we take its mean, which comes to 0.2 ton. So that was the step number 1. We have calculated the mean. Now we have to apply the formulas to find out the limits of the dispersion, the shift chart, as well as the dispersion chart. And as I said earlier, we are going to do both of them simultaneously. Let's do this shift chart first. The formula for the shift chart, which in this case is X bar R chart, this is X bar, this is R, therefore the chart is known as X bar R chart, is X double bar plus minus A to R. X double bar is this figure over here, and R bar is the mean range, which is over here. So what is A2? That we have to find from the tables. Again, X double bar, 0.937. This becomes the center line of the chart. R bar is 0.2, which is over here. N is the sample size. We have 5 blocks, so this is the sample size. This is not the sample size. This is the number of samples. Sample size is here, 1 to 5, 5 sample size. And A2, which is 0.577, found from the tables, and let's find it. This is the table. As you can see, it is headed 3 sigma constants for shift and dispersion charts. We have to find the value of A2, and the argument in this table is the sample size. The sample size for this particular case, remember 5 blocks, so it is 5. It is sample size, not the number of samples. So sample size is 5, and against this sample size, we find a figure of 0.77 under A2. This is what we require. So we simply plug in these values. In the formula, we know now everything. X2, A2, we have just found 0.577. R bar is 0.2. And we just put in the figures and get the answer. So the upper control limit of this chart is 1.052 ton, and the lower limit is 0.821 ton. Before we draw the chart, let's work out the limits for the dispersion chart also. The formula for dispersion chart, or firstly, what chart to be used? Since it is X bar R chart, the corresponding chart for dispersion is R chart. And the formulas are, for the upper control limit, we multiply this mean range with this constant or coefficient, and for lower control limit, we multiply it by this. So R bar again 0.020, and in this chart R bar becomes the center line. In this chart the X double bar was the center line, or in other words these figures become the center lines of their respective charts. So let's head back to the table again and find out the values of D4 and D3. So here we are against a sample size of 5. We have D3 0 and D4 2.114. So we can now put in these values in the formula. D4 was 2.114 multiplied by range mean, this one here, and we get 0.043023 ton as the upper limit. And since D3 was 0, so the lower control limit becomes 0. Let's see how we now draw the chart, which is the next step. We have found the center lines of the two charts, the upper control limit, the lower control limit. So let's see how do we draw the chart. For this chart, the shift chart, we will be plotting these figures, which are the sample means. We will not be plotting these, but these figures here, which are the sample means, or the X bars. And for the dispersion chart, we will be plotting these figures. And as I said earlier, this is the center line for this chart, and this is the center line for this chart. Let's have a look. This is the chart, and let me show you how this has been drawn. We have already worked out these two figures in the last slide. First of all, the sample numbers 1 to 6 are plotted along the x-axis. So 1, 2, 3, that essentially is sample number 1, sample number 2, all the way to sample number 6, because we have 6 samples in this question. And on the vertical scale, we plot the breaking strength. Which breaking strength? This is the breaking strength. Next, we plot the center line. X double bar is the center line, so it comes here, 9.937. Next, we plot the control limits. We had found the upper control limit to be 1.052 and the lower control limit to be 0.82 ton. The next stage is to plot the data. As I said, for X bar R chart, we plot the means. So the first mean, or the mean of the first sample was 0.928. We have plotted that. The mean for the second sample was 1.060. This is plotted there. And likewise, we plot the rest of them. The final point was to interpret the chart. Indicate if the process is under control or if it went out of control. Now, if we look at this chart, this process went out of control as far as truck number 2 is concerned, where it crossed the upper control limit, and in case of truckload number 3, in which case it crossed the lower control limit. So based on this finding, we'll reject the blocks which have arrived at the site in truck number 2 and truck number 3, and we are going to accept those or the other 4 trucks. So this is the practical application of these charts. This was the shift chart. Let's look at the dispersion chart. It is plotted much in the same way. These limits we have already worked out. We already know that this is the center line, this is the upper control limit, this is the lower control limit. Again, we plot, for plotting the chart, first of all, we plot these samples over here, and the limits 0.423 over here, the center line 0.020 over here, and of course the lower control limit 0 over here. So the limits are plotted. center line over here, upper and lower control limit. The next stage is to start plotting the data. And the first range is 0.20, which we plot here, then 0.1 here, 0 here, and so on and so forth. So this is the shape of the curve. So this is the first range, and then we can continue plotting the other ranges. As can be seen, this process remained under control. At no stage, the dispersion went out of control, which means that the blocks which were manufactured basically were very close to each other as far as the breaking strength is concerned. As I said earlier, shift and dispersion are the flipped sides of the same coin. They are conjoined twins. They cannot exist without each other. So whenever we make charts, shift and dispersion charts, we always put them one above the other and use the same scale, exactly the same scale, so that we can draw meaningful comparisons. This is our shift chart, this is our dispersion chart. So we can start interpreting it now that, well, over here we find that the breaking strength, the shift is smack on the center line, and not smack on the center line, but just slightly off the center line, and shift is on the, and the dispersion is on the center line. That was truck number 1. In truck number 2, the shift went out of upper control limit. But on the contrary, the dispersion decreased from 0.2 to 0.1. Now, what does this imply? This implies that though these blocks were over strong, the normal, the breaking strength of these blocks fell very close to each other. The only problem with them was they were extra strong. Well, that's a separate debate. Where is it better to have extra strong blocks? That's a separate debate. I would like to avoid that for the time being. With truck number 3, we found that whereas this was extra strong truck, this was extra weak, because the sample mean shifted way below the lower control limit. But as far as dispersion is concerned, it is 0. That means all the blocks were of the same strength. In the next case, we found that this truck was within limits as far as shift was concerned, towards the higher side, slightly towards the higher side from the center line, and the dispersion was smack in the middle on the center line, 0.2, or the range. Then comes truck load number 4. We find that again the supply is much better. The shift, the mean is very close to the center line, and some problem though with dispersion, although it is still acceptable. It is very close to the upper control limit, but it is still within the limits. And finally, I haven't indicated that through space limitations. In the next truck load, the braking strength is ideal. There's no shift. It is smack in the middle. But dispersion, there is some dispersion slightly towards the higher side, better than the previous truck, but still within control. So this is how the data or the control charts are interpreted. It is always a good idea to visualize things out of the statistical domain as if they were real life figures. So I have tried to make an attempt to explain to you this concept of shift and dispersion charts by taking you through a visualization. Here, I'm going to take the same two graphs, same two charts, and their data. This data, I'm going to take the same data and the same two charts into this visualization. So here are the two charts. Remember, this was the shift chart, which had gone out of control in truckload number 2 and truckload number 3. The other fours were fine. Remember this type of figure for dispersion, which remained in control. So what I have done over here, imagine this to be a runway or a highway. This is the center line of the runway, and these are the control limits for shift and dispersion. And what I'll do is convert these charts into bell curves and see how the bell curves look like when representing these two charts. So here is the data. In the first case, the sample mean was 0.93 and the range was 0.020. So here we are, the sample mean. So that our bell curve is sitting almost on the center line. So here's the bell curve sitting on the center line with a range or a dispersion of 0.02. In the second case, the sample mean went way to the side, 1.06. And its dispersion or range reduced to half. So that means because the dispersion has reduced to half, that means this bell curve is going to, number one, because of dispersion, become slim and tall. However, it is going to go outside the upper control limit. This is the upper control limit, 1.05. So it has gone out of that limit, and this is how it will look like. So it is slimmer and taller, but unfortunately, it has gone outside the upper control limit. And that is why we had rejected this, though it's a very good product, as can be seen, low dispersion, tall graph, very good product, but we rejected it because it went outside the upper control limit. Truckload number 3. A drastic correction can be seen here. Now it has gone in the other direction. The mean is 0.080. If we look, the lower control limit is 0.2. So it crossed 0.82. And what about dispersion? Zero dispersion. So it was an excellent product. Our bell curve had no dispersion. It became very tall and slim, but it had shifted drastically outside the lower control limit, meaning thereby it was a very weak truckload, and therefore it was rejected. See, it's very tall because it has no dispersion, but it is weak with a mean of 0.080. It means it is weak. Therefore, this too was rejected. Number 4, again a correction, and this time the truck has given us a mean, or the sample has given us a mean of 1. This was 1.05, this is 0.094. So this bell curve is going to lie in between this green line and red line, in between the upper control limit and the center line. And what about range or dispersion? 0.2, so it is going to have the same dispersion as the original. So it is going to sit over here, and it is going to look like this. 5th, it has gone towards the center line, crossed the center line and gone towards the lower control limit, but very clear of lower control limit. But dispersion, range 0.4, dispersion has become double than this. So this this graph, this bell curve is going to sag and flatten. Although it is going to be very close to the center line, this is what it is going to look. It has flattened, but it is sitting close to the center line, but it has sagged because of high dispersion. The next 0.9, that means this bell curve has come back to close to the center line. In fact, it has crossed the, yeah, it stays short of the center line, 0.90 here. And again, it continues, sorry, we're talking about this last one. So it comes straight back to the center line, which was 0.93. Dispersion is still high, though less than this. So it is going to become slightly taller than this and less obese than this. But it is going to sit right on the center line. So this is how, this is a visualization of what is happening to the shift and dispersion process. Think of bell curve as a worm, as a living thing. And if it was a living thing, this is how it would behave. It would keep moving left and right, as I showed you on the Excel sheet, and its height will grow or shrink, and likewise it is going to get flattened or get smarter depending upon the state of dispersion. So that was X bar R chart and R chart for shift and dispersion respectively. And the governing argument was the sample size. In this particular case, the sample size was 5. Now let's transition where the sample size is much bigger. On a production line, a sample of 12 items is taken from after every hour, and the items are weighed. The result of the last 9 inspections are tabulated, develop shift and dispersion charts if the plant is producing a 3 sigma quality level. So what do we have here? N. The sample size is 12 and the number of samples is 9. Because the sample size is greater than 9, we will use X bar chart with standard deviation this time. And the corresponding dispersion chart would be standard deviation chart, or the S chart. Here is the data. 9 inspections. These inspections are samples, so 9 samples listed. And sample size 12 as indicated by the number of items from 1 to 12. The procedure is exactly the same. We make 2 columns. Again, the first column is as for the previous chart, X bar R chart, we take the sample size, the sample mean. So we add them all up, divide them by 12, and we get the sample mean X bar. And we find for all the samples. The second column, we find standard deviation of this sample. In the previous case, we took the sample range. Here, standard deviation. The standard deviation is best found on a spreadsheet or using a scientific calculator with a statistics feature. It can be worked out manually, but in this example, where there are 12 items, it can easily take about half an hour to work one standard deviation. On a spreadsheet, it is very easy, very quick. So here we are, this column is for sample means and this is for sample standard deviation. As we did last time, we take the mean. So this, it becomes X double bar, that means bar of the bar or mean of the mean, or X double bar, and this becomes the sigma bar. So again, the rest of the procedure is exactly the same as for the previous one, except that we have slightly different formulas. Instead of A2, we have A3, and instead of D3, D4, we have B3, B4, as shown here. These are the limits of X bar S chart. That means X bar with standard deviation. X double bar, as usual, the mean of the mean, which we found out. This is the mean standard deviation, which we worked out. And for X bar R chart, we had A2 over here. For this chart, we have A3. So let's find out what this A3 is. Remember, the sample size is 12. So we enter this chart at n is equal to 12, and we find that A3 has a value of 0.886. So we simply enter this value in the formula. We have got everything now, 0.886, 45.13 from the last slide, 3.038 also from the last slide, into the formula, and we get an upper control limit of 47.82, was it grams? Yes, it was grams, and lower limit 42.44 grams. So this is the shift. Dispersion, these are the formulas. Upper control limit, this time B4, mean of standard deviation. In case of the range chart, R chart, it was D4. And instead of standard deviation bar, it was range bar. And for lower control limit, it is B3. Let's look at these figures again from the same chart. B3 is 0.354 and B4 is 1.646. So we enter these values, 0.354 and 1.646 into the formulas, and these are our dispersion limits. Upper control limit is 5 grams and lower control limit is 1.08 grams. Like we did in the previous example for range, X bar range and range charts, again, these charts are put one above the other to appreciate how the things have gone. As you can see, it is a very nice control process shift-wise, and so it is for the dispersion process. Dispersion in both the charts, the process remained under control. I'll interpret one or two samples for you. In this case, we find that the sample mean was just towards the higher side of the mean, but well within the limits. And the range or dispersion was on the lower side, slightly towards the lower side, but still within the limits. We had an excellent example, sample mean next time, very close to the center line. And the dispersion went slightly on the higher side, but still within the limits. But then this was a very weak sample where the sample mean dipped below the lower control limit. So the process went out of control. Dispersion was fine, low dispersion, but because of this shift going out of control, this sample or all the deliverables coming out of this shift or this R, because this inspection is being carried out per hour, everything produced by this shift was rejected because the sample has failed. Rest, it is all smoothing, nicely flowing data either side of the center line, both in case of shift and dispersion. That more or less completes the discussion on control charts for shift and dispersion. I just want to show you this slide, which is a snapshot of all the 4 charts we have done. This is the center line. These are the charts for shift, and these are the two charts for dispersion. Remember, X double bar plus A2R for shift, or X double bar plus A3 sigma bar for shift, depending upon the sample size. So here, if the sample size is less than 10, then center line in either case, center line in both cases, whether the sample size is 9 or less or more than 9, it remains X double bar. That is, mean of the means is always the center line. Then something plus becomes the shift, and something plus becomes the upper control limit of the shift, and something minus becomes the lower control limit. What is that something? That something differs for the two charts. If the sample size is 9 or less, then the coefficient or the constant we use is A2. And if it is more than 9, the constant we use is A3. In this case, we use range bar, and in this case, we use the standard deviation bar. Coming to dispersion chart, again, depending upon the sample size, we have different charts. If the sample size is less than 10, then the constant to use is D4. And if it is greater than 9 or 10 or more, it is B4. Over here, we use the range bar, and over here, we use the sigma bar. The center line of these charts is this thing here. So if it is R bar becomes the center line. If it is sigma bar becomes the center line. So it provides a good snapshot of the shift and dispersion chart. With that, we come to the end of this session. That leaves us with the defects and defective charts. Oh, by the way, I forgot to show you this slide. This is a slide where the entire dynamics of the group charts are put all together. In fact, all you need is this slide to work your way through any control chart. First of all, you have to put the data in this grid. This is the number of samples, and this is the sample size. So just enter the data into this. Then make two columns. The first column is always the sample mean, and at the end of which you take the average again to make it mean of the mean, or X double bar. The second column will depend upon the sample size. If the data is up till here, 9. If the data is up till here, then over here, the argument is range. But if the data goes beyond 9, it is 10, 11, 12, 20, 50, 100, then the argument here is standard deviation. In either case, we take the mean. And then we proceed as we have already done, work out these figures, put them in their respective formulas, get the upper and lower control limits, plot the chart, plot the data, and find out whether the process remained in control or it went out of control at any stage. Now we come to the end of this session. That leaves us with defects and defective charts, which is the subject of next session. Until then, Allah Hafiz.